Students, now we can proceed and we can form the equation for the 4 number of loops similarly. Similarly, for n is equals to 4, that is third overtone and the fourth harmonic. Now we can write the general term, not the general term, for the n is equals to 4, that is f4 is equals to, we have f2 is equals to 2 times of f1 and we have f3 is equals to 3 times of f1. Now we can write here f4 is equals to 4 times of f1 for the 4 number of loops, where we know that f1 is equals to the fundamental frequency, which is equals to the V over 2L, and so on. Now for the general term, for general formula, we can write here the Fn is equals to n times of f1, where n is equals to the number of loops generated in the string and f1 is equals to the fundamental frequency. Which is equals to the V over 2L. Students, for the examination, this general term is not needed. Basically, only the sequence of the generation of the number of loops and how can we generate or how can we find out the frequency by the wave equation, it is important, not the general term. But if you learn about the general term and keep in your mind this general term, you can easily understand the question and proceed in the question according to the given conditions. Okay, students? Now we'll discuss about the relation between the number of loops and the frequency and the wavelength of the waves. As we know that according to the formula, students, in the topic of stationary waves in a stretched string, we have started that topic from the laboratory experiment or the laboratory experiment apparatus, in which we have the vibrator and a string horizontally connected with this vibrator, and this oscillator can move vertically upwards and downwards. By this movement we can generate the stationary waves in this string. And as you can see in this diagram, this string is connected to the hanging mass, which has a weight W is equals to mg. Because of this weight, we have generated a particular tension in the string. Because this string is a single string, so the tension will be the same for all of the string parts, okay, the horizontal part as well as the vertical part. It means if we have the tension T generated in this string, and when we start the oscillator and the stationary waves are formed, the speed of those stationary waves is affected by this tension generated in the string, because if we change the hanging mass value, the number of loops in this string will also be changed. It means the frequency and the speed and the wavelength will also be changed because of the change in the tension. And if you use the string of the different thicknesses, the speed can also be varied for the stationary waves generated in those strings of different thicknesses. Now we'll discuss about the formula. that relates the wave speed, that means the speed of the stationary waves, and the tension in the string and the mass per unit length. And now first of all we will discuss about the mass per unit length. What is mass per unit length basically? Mass per unit length shows the thickness of the string. If we have the thick string, that means of the greater diameter, so it has the greater mass per unit length, and if we have the thin string which has the less diameter or the cross-sectional area, so it has the less mass per unit length. To calculate the mu, that is the mass per unit length, we can use the formula here, that is mass of the string divided by length of the string. This mass of the string can be calculated in kg, and length of the string is measured in meters. So we have the SI unit for the mass per unit length. Mass per unit length is kg per meter. Now it is the formula by which we can relate the wave speed, the tension in the string, and the mass per unit length. According to this formula, and students, the derivation is not in our syllabus, we will discuss only the formula and the relation between the quantities. According to the formula, if we take the constant cross-sectional area of the string, that means the constant mass per unit length of the string, there is a direct relation between the string and the tension. So we can write here the V is directly related to the tension in the string, and if we use the constant tension generated in the string, and we are changing now the thickness of the string to study the waves generated, the speed of the waves generated in the string. So there is inverse relation according to the formula, and we can write here the V is inversely proportional to the square root of mass per unit length. Okay students? Students, basically there is one confusion, because we have already discussed that the energy cannot be transmitted by the stationary waves between the 2 points, and we have already discussed that the profile of the stationary waves can be seen in rest. That's why these are called the stationary waves. So what will be the significance of the term speed for the stationary waves? Basically, significance of speed for stationary waves. We know that the stationary waves are formed due to the interference between the incident and the reflected waves, and the antinodes are formed due to the constructive interference, and nodes are formed due to the destructive interference. That's why we can define, or we can describe the term speed in the stationary waves like it is the speed of incident waves and the reflected waves. It is the speed of incident waves and the reflected waves. Thank you students. Now this topic is completed.